All right. At this point, you all should have, I hope, taken some time to try to figure out the answers to the practice problems on page 8 and page 9 of the correlation and regression packet. So please review, answer those questions, get together with your fellow students, see that you're on the right track. Make sure you understand the interpretation of the correlation. Make sure you understand the coefficient of determination and what it tells us about. Make sure, if you don't already know how to do this, that you've taken the time to meet with Andre and figured out how to use your calculator in order to come up with the Pearson R. I would imagine that it should take you no more than 2 minutes to enter the data for your X values and the corresponding Y values, and then have your two variable calculator spit out what is the Pearson R value. That value should match up to the Pearson R that can be calculated through using the Excel software. So again, I get in the mode of checking things by entering in this case, the height data, entering the weight data in, seeing whether if height is related at all to weight. You can see that for these 5 subjects, we've plotted each of these points, which represents the height and the weight for each 5 of them. There's then a line that's drawn here. Excel, in a matter of seconds, will give you this correlation. It will give you where we're going now with the line of best fit, the line that is drawn on these points so as to minimize the distance of these points from the line. And we also see this R squared. I hope that's flashing in your head saying, wow, this is the coefficient of determination. If I were to take the square root of this, I would get the correlation, all right? So the square root of 0.7548 should bring us back to our Pearson R. You're given a Pearson R, you square it, you now have the coefficient of determination. You have a coefficient of determination, you take the square root of it, and you get back to the R. The only thing that's tricky about that last maneuver is you need to figure out whether that R is positive or negative, since when you do square things, they all become positive, whether the R is positive or whether the R is negative. So again, finish pages 8 and 9. See if you can do this practice problem. See if you come up with this Pearson R. Check it with Excel. And the next place that we're going with this information is we're going to handle the topic of the line of best fit, as well as the error that is associated when we make a prediction using this line of best fit, or what we're going to be calling the regression line. So I think I'll bring us back to the PowerPoint slides and take us to, I think you left off right about slide number 37. So I'll go back to slide 37, and I will explain that when we have a variable, in this case, the variable is the sum of 3 skin fold measures. We think that that is related to the percentage of body fatness that you have. We can actually determine the percentage of body fatness that you have with minimal error by using techniques such as underwater weighing or dual X-ray absorptiometry. We then can take the sum of 3 skin folds that we measure on your body, and we can relate this sum of 3 skin folds to the percent body fat determined by, and you can label this axis the y-axis or the criterion variable. So in this case, the criterion or the gold standard measure might be percent body fat determined by DEXA or underwater weighing. So our X variable, our Y variable, our independent variable, our dependent variable, our presumed cause, our presumed effect, and sometimes this dependent variable is referred to as the criterion variable. So the cool thing about a line of best fit is you draw this line, again, to minimize the distance from all of these points to that line, and this is what we call the prediction line or the line of best fit. If there's a line that we can come up with, and if these points aren't too spread out from the line, We then can take a person whose sum of 3 skin folds we know, and we can then come up to this prediction line and see what is the predicted percentage of body fatness given those skin fold measures. So that would be the application in terms of prediction. Here's another prediction example that we use a lot in the homework assignment and on exams. In this case, we have scores for people on 2 variables. This is body weight, and I'll inflate this so you can see it a little bit better. This is the body weight on the x-axis. The y-axis is the number of pull-ups that the subjects were able to complete. What you see here is that there are 10 dots that indicate data for 10 subjects. It looks like we had 2 people that were 170 pounds. One of them was able to do, it looks like, I think that's 4 pull-ups. Another one was able to do maybe 5 or 6 pull-ups. So we have these 10 data points. This line of best fit that we call the prediction line, it's also called the regression line, is drawn to minimize the distance between the data points in the line. You can see that I could have drawn a number of lines on this scatter plot, but this particular line is called the line of best fit because it minimizes the distance of the points to the line. The general form of the equation for this line of best fit or prediction line is y hat, which is indicated by these symbols, or what we call y predicted. So you want to label this y predicted or y hat, and that's going to be a function of b times x plus c. In this case, b is equal to the slope, and c is equal to something that we call the y-intercept. B is the slope, c is the y-intercept, and this is a general form of an equation now that's going to allow us to predict this y, predict this outcome based on the value of our x and these numbers b and c that are true for this particular equation. Remember that this over here is y predicted, or essentially it's y hat is the little symbol here, and we're going to see in the next slide that we also can have that line of best fit. The general form of that line of best fit looks something like this. Y predicted, which is indicated by the apostrophe here, just another way to write this, is a function of some number b times x plus c. B is given is actually the slope of the regression line. Many of you have already learned that slopes of lines are really how much change of x do you get, how much change of y do you get for a given change in x. It's the rate of change in y per unit of change in x. This is the slope, and b is what you want to label the slope in this particular line of best fit or regression line. C is the y-intercept term. This is a constant, and the y-intercept essentially is what is the value when x is equal to 0. What is the point at which that line is going to cross the y-axis, essentially the point where x is equal to 0. What is that y value? We call that the y-intercept. This is the y-intercept, and an equation for the line will have a value for b, it'll have a value for c. Then what you can do is you can plug in any predictor x, and you can see what is the outcome or the predicted y value. So here's going to be the deal. We're going to try to predict things, but unless there is a perfect negative or a perfect positive correlation, that is, all the data points are actually right on that line of best fit, there's going to be error in the prediction. And what we want to remember is that the most common way that we're going to express error is what we call the standard error of the estimate. The SEE, or the standard error of the estimate, is going to give us information about how accurate our prediction is. Essentially, a lower error, a lower SEE, is going to mean that those points, which are actual data points, are very close to the line of prediction. So low SEE, low error, means that we have a more accurate prediction. Essentially, in the scattergram, the points are closer to the line. So in order to understand that fully, we're going to start with just a basic understanding of error. Another term for error is what we call residual. If you recall, the guy who was 140 pounds, he is predicted by this equation here, and what you're going to see is that y predicted is equal to b, or the slope, times the x value, which in this case is body weight, okay? You add to that the y-intercept, which is 25.888 in this case. We see that this guy who walks in the door that's 140 pounds, based on this line of best fit that we've drawn, based on these other data points, we predict that this guy is going to do 7.97 pull-ups. Well, he comes in and kind of blows it out of the water here, because you see his actual data point is up here. At 140 pounds, he actually did 12 pull-ups. So his individual error, okay, so we're just going to use the term E now by itself. His individual error is his actual score minus his predicted score, and our answer is going to come out in our units of measure for y. In this case, it's the number of pull-ups. So for someone that is 140 pounds, we predict they're going to do 7.97 pull-ups. He actually does 12, so the error in this prediction is 4.03, and the units here are pull-ups. So this is the concept of error. We're going to expand on this, and we're going to learn how this error and understanding this error can give us an idea of overall how good our prediction is. So I'm going to turn now to the standard error of the estimate. If we look at the slide after next, we're going to see an example of how we actually use this standard error of the estimate when we predict people's body fat, because it's very rare that you have the luxury of doing underwater weighing or luxury of determining percent body fat by using DEXA. Instead, we use a prediction equation, and that prediction equation was built on the relationship between the skin fold thicknesses of hundreds of people and what their corresponding actual percent body fat is, using a very accurate technique. Once we have this prediction equation, we can then, see that we can estimate what people's actual percent body fat is using some of these criterion or gold standard methods, and we hope that the error will be minimal. So let's review now what is called the standard error of the estimate. In your handout packet, you see that it can be symbolized as S sub y dot x. Just different textbooks are going to use different terminology for this. And what I want you to recognize, first of all, that the standard error of the estimate is error. And error is bad, because error represents the scatter or the deviation of the points around the line, so if the points were all on the line, we would have zero error, okay, and we would have a perfect prediction. But the further those points are from the line, the further those actual points are from the prediction line, that's going to be more error, and that's something that we don't want. So if there was something that I had to memorize on this unit, because I will ask this again, and it should sound a lot like what we've covered previously in the course, is I could ask on the exam, what does the standard error of the estimate actually represent? Well, the standard error of the estimate represents the average deviation of the real scores from the prediction line. It represents the average deviation, okay? It is, therefore, the standard deviation of the error. It is the standard deviation of the residual scores. So the less error you have, the closer the points are to the line, the less spread around the line there is, and the lower the standard error of the estimate. Okay? So let's go back to our example. Here we see skin folds, and skin folds are often used to predict body fatness. If these points are very close to the line, the error is going to be very small. How do we index error? We can use the standard error of the estimate. The SEE, you'll recall, is the average spread of the actual scores around the prediction line. It is the standard deviation of the errors. It is the standard deviation of the errors. So, somebody comes in and they say, take my skin fold measures. Would you estimate my percent body fat? So we come along here, we sum up their skin folds, and we find, wow, the sum of your skin folds is 76 millimeters. We then come up here to our prediction line and say, based on the 76 millimeters of skin fold measure, I predict your body fatness is this. Okay? So we have data, we have predictors, and we have an outcome here, and we're making a prediction. But you can see, even based on these original data points, that not everybody is going to have a true skin fold, a true percent fat that is on this line. Oftentimes there is error. We can index this error by the standard error of the estimate. The error in prediction, all right, is indicated in this way. Now, I don't know about you, but if you turn this sideways, I hope all of you see it's like there's a little normal curve here, there's a little normal curve here, there's a little normal curve here. And what you're going to see is whenever you have someone that walks in the door, no matter what their skin fold measures are, you're going to sum those together, and from the sum of those skin folds, you're going to predict what their percent body fat is. A higher sum of skin folds, you're going to have a prediction of a higher percent fat. But what I want you to realize is this line was drawn to minimize error. So what we're going to see is this line is our best guess of what people's true scores are. But sometimes there's that guy, remember, that weighed 140 pounds and you predicted he was going to do around 8 pull-ups and he actually does 12. There's sometimes when people are going to be have very different values than what you've predicted. So we get an idea of the degree of error by looking at the standard error of the estimate. The standard error of the estimate says, hey, I'm going to predict your score here based on your sum of skin folds. This is the percent body fat I'm going to predict for you. But you'll notice that on either side of this, there is error. Most people whose skin fold measure is out here are going to have actual percent body fats that are right in this region here. There'll be a few people that have actual percent body fats way up here at a very high value. And there'll be a few people who have percent body fats that are way out here, a very low value relative to the prediction. But most people, i.e. the normal curve, most people will have an actual percent body fat that's pretty close to the prediction. How much error is involved here in this prediction? We can index that by the standard error of the estimate. The standard error of the estimate is the standard deviation of the errors around the prediction. The standard error of the estimate is the standard deviation of these errors. So moving on here, this is actual data. We know in general across many studies that if you sum skin folds together and maybe take a sum of 3 different skin folds measured throughout the body, and let's say in this case that you measured and summed those skin folds up and they were 40 millimeters. we could see here that based on that, and this line of prediction, which has been drawn based on many, many subjects, that we would predict your body fatness to be 20% body fat. But there is error, and there is published information showing us that the standard error of the estimate when predicting percent body fat by sum of skin folds is actually equal to plus or minus 3.5% body fat. So to visualize this now, we're going to come back to our graphic, and you're going to see here that although we've predicted that this person is 20% body fat based on the sum of their 3 skin folds, in actuality, if we go up plus 3.5% from that, and we go down 3.5% from that, in other words, we go up 1 standard error of the estimate, and we go down 1 standard error of the estimate, it's just like a standard deviation. And if you'll recall, 68% of the time, the scores are within approximately plus or minus 1 standard deviation of the mean. Well, the standard error is the same thing. The standard error of the estimate, though, is not error around the mean. The standard error of the estimate is the error around the prediction. So we can say that although we predict your body fat is 20%, 68% of the time, your actual body fat is going to be between 16.5 and 23.5% fat. So that, in a nutshell, is an interpretation of the standard error of the estimate. It's kind of like a standard deviation. But now, instead of average deviation around the mean, we're saying what's the average amount of deviation of the actual scores around this prediction line. So, here's what we tell Joe. Joe, we estimate, based on your skin fold assessment, that you're 20% fat. The standard error of the estimate for this prediction is 3.5% fat. What this means is there's a 68% chance that your actual body fat is between 16.5 and 23.5% fat. I don't know about you, but if I were Joe, I'd be concerned. Because remember, 2/3 of the time, when we tell you, 68% of the time, 2/3 of the time, we tell you your body fat is 20%, it actually is between here and here. Which means that 1/3 of the time, when we tell you your body fat is 20%, all right, 1/3 of the time, your body fat is actually greater than 23.5% or less than 16.5%. Very important that we understand how to interpret what is the standard error of the estimate. Now we can come up with a number for the standard error of the estimate by using this equation. This is the estimated standard error of the estimate, and you take the standard deviation of the y-scores, we already know how to find that, comes out of our calculator. We multiply that by the square root of 1 minus the coefficient of determination. So the SEE, which is also abbreviated S sub E, all right, is S sub E is equal to the standard deviation of the y-scores times the square root of 1 minus the coefficient of determination. So I'm asking here, how are the correlation and the SEE related? I hope you see, the higher the correlation, the higher the coefficient of determination, the lower this term will be. And the lower this term will be, the lower the error. I'll say it again. The higher the R, or the higher the coefficient of determination, the lower this term will be. Therefore, the lower the error in our prediction. Okay, now there's different names, of course, that are given to this term, the standard error of the estimate. It's sometimes called the standard error of prediction. It's sometimes called the standard deviation of the errors of predicting y from x. And sometimes it's called the standard error of regression. What you need to know is that very simply we can estimate what this value is and report to our clients, patients, and athletes how much error is involved in the test if we do the simple math that's involved in estimating the standard error of the estimate. Okay, the last topic in the packet that we'll want to discuss is multiple regression, and this is not very complicated. Instead of having a single predictor, instead of having a single x variable, we have multiple predictors. And the great example of this that we talked about in class was certainly we can predict your likelihood of succeeding in college if we have more than just your high school GPA. Oftentimes you're asked to take a standardized test like the SAT test because two predictors or multiple predictors will explain more of the variance in college success. So multiple regression, multiple prediction is using several x's, several predictors in order to estimate a dependent or y variable. So this is what it looks like. Here is our predicted value, but now we could use high school GPA, SATs, maybe you write an essay. Multiple predictors oftentimes will estimate this outcome, in this case college success, with less error than a single predictor. We have coefficients here, just like before. These are analogous to the slope in a simple linear regression. We also have a y-intercept term, just as we've seen before. So instead of little r, we're going to use big R. And big R is used to symbolize the multiple correlation, multiple regression R instead of a little r. And likewise, when we do the r squared, it's still called the coefficient of determination, all right? But we use a big R because we have more than one predictor. More than one predictor. Big concept here. Higher R squared, the better the prediction. The higher the R, the better the prediction. The lower the error, the better the prediction. Everybody got that? I hope so. That's a key concept. One example that I think is really interesting because I have a physiology background. I'm interested in muscle fiber types. We know that we have fast twitch and slow twitch muscle fibers. And one of the ways that we could figure out your muscle type is to stick a little biopsy needle, maybe into your calf, take some of the muscle out, and histochemically take a look at what was the tissue and the properties of that muscle fiber, and we could characterize it as fast twitch or slow twitch. But that hurts a lot, and it's invasive. We know that we are actually able to predict the percentage of fast twitch muscle fibers that you have. And one of the ways that we can do that, instead of doing a muscle biopsy, is we could use a predictor, in this case, a rate of fatigue. It turns out that fast twitch fibers are what we call fatigable fibers. They're going to fatigue much more easily. So we can actually give you a 30-second cycle test and see how quickly you fatigue. If you fatigue more quickly, you probably have a higher percentage of what we call these fast twitch fibers. These are your power fibers. We know, too, that fast twitch fibers are really good at generating force. So we could actually, and I encourage you to read through this entire slide, we could actually predict what is your muscle fiber type much better by using two predictors, okay, to determine what is the outcome. Okay, the outcome would be the gold standard, in this case, the muscle biopsy. And we could look at one predictor being your rate of fatigue, and the other predictor we could look at is how much force are you able to generate with your muscles. This would be a multiple regression approach, multiple correlation, multiple regression approach. In this case, we have we want to predict your percent fast twitch fibers, which are outcome or Y variable or dependent variable. And we're going to do that looking at the rate of fatigue. But we're going to add in another variable here. This is the second independent variable, and that's the rate of force development. And our hope is that we come up with a pretty good prediction without having to do a muscle biopsy on you. We do this all the time in our field, and you're going to have some homework problems that relate to this. In this case, we're predicting someone's VO2 max, and we're going to use 1, 2, 3, 4 different X variables or predictor variables. One of them is how much self-reported physical activity you have. Another is what is your body weight and height, what is your BMI. Persons with a higher BMI, by the way, notice the negative here, will have a lower VO2 max. People that are older will have a lower VO2 max. The sign of these regression coefficients indicate the influence on VO2 max. The more self-reported physical activity you have, the higher your VO2 max will be. And we use sex as well to report or to predict VO2 max, with males on average having about 10 mils per kg higher VO2 max than their female counterparts. If you're interested, I have a website here that you should click onto. You can see here, this is the Rockport walk test. We oftentimes give this to more deconditioned people to estimate their VO2 max. You go onto this little calculator, you plug in your age, you plug in your time, you plug in your body weight, and how long it took you, I guess, to walk 1 mile on the track. And we can come up with a pretty good prediction of what your VO2 max is. The multiple correlation coefficient, which is just like the little r, but now it's a big R because we have multiple predictors, is 0.88. And look at this. The standard error of the estimate is 5 milliliters per kilogram per minute. Okay, I'm actually going to stop here and go back to the packet, but I'm going to stop this video here so that you get a chance to maybe review these slides and get ready for the last of these video series.